Okay, thank you very much. Good morning, everyone. Hope you had a nice first day of the school yesterday. First of all, do you have any questions about yesterday first part? Yeah.
That it is gauge fixing, which is required, we are able to inspect the degrees of freedom in the sensor. Could we do the same with light quantization, for instance?
With the?
Light.
I'm not familiar with the light quantization, but
I don't know, maybe another way to choose non-covariant gauge, which has the same benefits that we're describing.
could be. Maybe you can.
Yes.
Okay.
Maybe more active than this gauge. You mean like yeah, I think it's similarly inconvenient.
Yeah, I would say maybe non-covariant things are usually inconvenient for computations. Yeah.
For example, in office paper in two-dimensional, it's like something like that. In that case, it's convenient because it's two dimensions. Okay. Otherwise, it's kind of messy.
Thanks, Ivano. Okay, so then we continue. Okay, so if you remember, yesterday we were basically and we ended the lecture by mentioning something about spin projectors in the case of the photon propagator, and the idea was basically to generalize the same procedure to the case of the graviton propagator, because our point was we derived the propagator like in several ways. For instance, in the Donder gauge by choosing the Feynman gauge fixing, and we got the formula in terms of eta Minkowski tensors, from which we said, okay, that's nice, but we cannot completely maybe see what is the number of independent components that have the pole at 1 over p square. And we said, okay, maybe we can try to see that explicitly by going to a non-covariant gauge. And we saw basically the other way of writing the propagator in the Prentke gauge. And this was just basically at the level of the propagator. Of course, also Paolo mentioned yesterday, one could see the independent degrees of freedom once we take an on-shell amplitude, which means, for instance, even if we start from the Feynman propagator, the Feynman gauge propagator, well, I don't need to write it here. This one. And then we have, even if we start from this, we said, okay, from just at the level of the propagator, we cannot really see how many are the independent components that will have a pole at p square equal to 0. But either we go to some non-covariant gauge to see that explicitly, or for instance, what we can do even at the level of this propagator, we could in principle say, okay, let's consider an amplitude where we take two stress energy tensors, T and T prime, for instance, two different stress energy tensor, and we can basically contract the indices of this propagator. So we compute an amplitude, right? Something like this. And of course, if we go in shell, which means p squared equal to 0, and we choose something like, as we did yesterday, right? Something which is oriented with the spatial vector along the direction. And we take into account of conservation law, which are this one, basically. And we apply, we basically use this in this choice of frame. It means that basically we'll have what? That T P0, 0 nu plus P3 T3 nu equal to 0, but these are equal, right? And up to a minus sign. So what we will get basically is that T0 nu is equal to T0 to 3 nu. The same for T prime. Using all these conditions and develop, basically looking at all the contraction here, in the end, one can show that what one gets, it's something that will only propagate the helicity that we saw yesterday, basically the cross and the plus, for instance. So you will only have something of this type. You can show. Well, the same. To mu. Let's just write it through this. Plus, cross and plus, and then you will have lambda rho sigma, something like this. Okay, so by using properties and so on, you can also show that in the end, this will be the only one that will contribute. But if you want to show it, I mean, you can do that. The point is that once you go on shell, the two degrees of freedom will appear in some way. Now the point is, okay, let's forget about shell. Let's just keep the propagator completely off shell. And let's try to write it in terms of these spin projectors, as we said yesterday. In the case of the photon, we said that we could introduce, given the vector, the photon vector, a mu, we could always decompose this in terms of like two projectors given by this expression. And the theta mu nu would propagate the spin 1, and omega would propagate the spin 0. But which spin 0 is spin 1? Basically the one that you would get when you, for instance, look at the representation of SO3. Because you can always write like a vector in terms of a 0 part, which is invariant under rotation, and the, let's say, 1, 2, 3 component that form one vector under rotation. And the idea was, okay, let's do the same also for gravity. So basically, we would like to introduce a set of spin projectors that allow us to project the field h mu nu in all its possible components. And as we said yesterday, h mu nu as a symmetric tensor can be decomposed in terms of a spin 0, another spin 0, I mean a scalar, then a vector, and a spin 2. And actually, let me also mention something, since there was a question yesterday about why this is possible. When I answered the question, I think I was not completely correct, as Fawad let me know this. So it's good to have also people can give like feedback afterwards, because what I said yesterday, you can look basically at the transformation of this object here. But actually, I should not write this. That's what I wrote yesterday, which is true, but it's true only for the Lorentz transformation, because more generically, this is true for G mu nu. Right, this is the transformation for G mu nu. And then we have to rewrite that for this transformation here. And since we are working with the rotation, which are basically Lorentz transformation, we are basically taking this. Okay. Only in this case, then I can put here H and H. Okay. So I didn't say that. So I wrote it something that looked correct, but the way I was saying it, I think it was not completely correct. Okay. So you can write it for H when you have lambda. Otherwise, more generically, you need to be careful. You need to put the G, the complete metric. And of course, now if you look at the basically the 0, 0 component, the trace, the 0i and the ij, they will transform as a scalar spin1 and spin2, just by following the logic of yesterday, right? And so the idea is to basically introduce spin projector also for these components. Now, the story, of course, can be made very short without going into details of computations, and that's what we're going to do. So basically, I will just write down which are the projectors for these components, and trying to see whether these form a basis or not for tensors that are with 4 indices and symmetric. The answer will be no, actually. So we need to add something else. And then rewrite the kinetic operator in terms of this basis. Write an ansatz for the propagator in terms of this basis with some unknown coefficients. We plug everything in the relation like kinetic operator times propagator equal to identity, and we will determine the unknown coefficients and find the propagator. That's the logic. Computation will basically be needed to really show this, but we will just give the answer. So let's maybe, yeah, it's the same. Let's do this. Okay. So just one way, for instance, to see how one could get the projector you want is the following. You see, we have an h mu nu, and you know that a vector can be decomposed in that way. So what you could do, you could say, okay, I decompose each of the indexes of this h mu nu in the same way. So I write something like this, for instance. And I use something similar for the other index. Nu, sigma, nu, sigma, h, rho, sigma. I can do something like this. Okay. Now, since I know already the result, I will tell you what happens here. Basically, you can use now symmetry properties and so on to write this combination in a specific way. So you can write the following. I will just write the expression every what they are. You can write everything like this. There will be some spin 2 deduct on the metric plus a spin 1 over a projector deduct on the metric plus 1 spin 0 that is sometimes called 0s deduct on the metric, and then there will be another one that sometimes called 0w deduct on the metric. And these two are equal. So basically, by using symmetrization and so on, you can show that basically since this has to be equal, there should be a completeness relation that must hold, which is the following. That the sum of these has to be equal to identity. And the identity, remember, was this one in the space of symmetric tensor with the 4 indices. And what are these projectors? Basically, the spin 2 is this one. There will be combination of theta, mu rho, nu sigma, plus mu sigma theta nu rho minus 1/3 mu theta rho sigma. Then there will be a spin 1, which is a bit longer, but it's a combination of theta and omega up to all possible symmetrization of mixed indices, which is the following. You have theta omega with this combination into mu rho nu sigma, then you have mu sigma nu rho plus theta, and you change mu and no like this, and plus you have the other, change now rho and sigma. Nu, mu, rho. Voila. And finally, you have the 0s, which is 1/3 theta mu nu theta rho sigma, and then you have this 0w, which is mu nu, omega mu nu omega, rho, sigma. Now, you can just check that if you plug this expression inside here, you will recover just this one or this one. Okay, they just satisfy this complete relation. But why one write this type of expression? Because one can check that basically they really project along these spin 1 and spin zeros components by taking the trace of these objects. Again, because since we have projector, which satisfy idempotency, which means that if you take the square of a projector, you get the projector again. And actually, let me say they are also orthogonal. So I can write this. Huh? So since they are they satisfy this idempotency relation, their trace will be somehow equal to the rank in terms of matrices. In this case, we have this type of operators, more complicated. So we expect that the trace will give us basically the rank, which is the dimension of the representation of the irreducible representation. And since the dimension is 2j plus 1, where j is the spin, we should expect that the trace give us 2 spin plus 1. Okay, now, you can check that if you act with the identity, which is this object here, on each of them, okay, let's call actually the identity. I've never done it so far, like this. If you act with the identity on these objects, what you will get is the following. Let me do this. Mu, nu, rho, sigma. If you act with this identity, you will get 2j plus 1, always. And when you have 2, you will get the spin 2. When you get 1, you will get the spin 1. And for the 2 spin zeros, you will get the spin zeros. So that's why these projectors really project on these components. So if we manage now to rewrite the kinetic operator in terms of this and invert it, would be nice, because then we get the propagator in terms of this, all the spin components that are present of shell. And you should expect all of them, because of shell you can have everything, right? All the components can be there on shell, off shell, physical or unphysical, where physical I mean on shell. Okay, but the question to ask first is, in order to write down the kinetic operator in terms of this, I need to understand whether they satisfy or not a basis. Otherwise, I cannot write them. I cannot write. Do you remember the kinetic operator that we were calling? I was using this. We were calling it in this way. That's like the one already with a gauge fixing. We were calling kappa tilde. We would like to write this basically in terms of a linear combination of these operators. In QED, so in the case of the photon, it was enough to consider just the two projectors, because they were not only basis of complete projectors, they were also a basis for symmetric two-rank tensors. But in this case, unfortunately, I don't know, but these 4 terms are not enough to close the basis. Why? Because, do you remember which were the independent, up to symmetrization, independent terms that you can have that are with the 4 indices and so symmetric in this sense? Yeah, they were these ones. We have this combination of eta, then we had the one with mixed indices, which was this one. Then we had the one with p mu, p nu. So these are all the possible Lorentz invariant one you can have. Of course, you need to assume Lorentz invariant. Yeah, this. Then you can also have the mix there. And then you can have, in principle, this moment as well. Right? Now, if you look at the expression of these objects, theta, 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 and so on, the only one actually that is missing, that you will never encounter, is this one. You see, you will never have that one. You never have basically a term of the type theta mu nu times omega rho sigma. There is no such term. You have theta omega, but they're with mixed indices. You don't have mu nu rho sigma. You have always mu rho or nu sigma, or nu rho, and so on, okay? So what you have to do, you have to add another object that closes the basis. And the object that you have to add is this one. Sometimes called cross, it doesn't matter. Okay. SW, and they usually write. It's not needed. Let's make the story shorter. Let's call it just in one way. We call it as 1 over 3, 1 over square root of 3, mu, nu, omega, rho, sigma, plus the other. Mu, rho, sigma, omega, nu, rho. Okay, this is the object. Once we put that, then we can really close the basis. Now, what we should do, we should basically express the kinetic operator in terms of all these 5 objects. And if we do that, we can basically write the kinetic operator as follows. Here I'm working in the Donder covariant gauge fixing, okay? We will have the spin 2 part, then minus 1/2, the speed 0 has here, mu nu rho sigma, C, which is the gauge fixing parameter, mu nu rho sigma, plus 4C minus 3 over 2 P0W. And then we have also the one that was missing, which is this 3 over 2. Okay, this is what you get. By the way, here I never said references and so on. Sorry, I should have said the first lecture. There are good references for part of the things I'm saying as books. And one is a book by, for instance, Roberto Percarci from SISA. It's called Covariant Quantum Gravity and Introduction to Atomic Safety, I think. And for instance, you can find also this derivation there. He does it in the another gauge. So you can really find the derivation with all the details. Another book is also very nice, I think, is the one by Buchbinder and Shapiro, which is very recent. It's called Quantum Field Theory, I think, and the Introduction to Quantum Gravity. I can give you the references actually, maybe. At the end, I will write better the references. It's from Oxford Press and so on. And there are also various lecture notes on the internet. And one by Donoghue is also nice, I would say. It's called EPFL Lectures on General Relativity as a Quantum Field Theory. So, yeah. But when I will send the notes, I will also put the bibliography of things to follow. But anyway, now we have this operator. What you have to do, we have to invert it as we did with the other things. We just have to plug it in a relation with the identity, like G times kappa equal to identity. I put an I for convention as well. And what you get if you do that is the following. I did, here is 1 over C. I copied part of the propagator and part of the, sorry, just a second. This is C here. Sorry, let me write the kinetic operator. Yeah, I was copying things. So you have here 1 over epsilon, 3 over 2, 1 over C minus 2, P0S. Okay, let me write it again. I didn't even look what I was writing. So the kinetic operator, if you write it, is the following. Spin 2 part plus 1 over C, spin 1 part. Then there is 3 over 2, 1 over C minus 2. The 0 part S. Then there is minus plus 1 over 2 C. P0W. And then we have 1 minus 2C P cross. Okay, this is the kinetic operator. Okay, now you can invert it and you get the propagator, which is actually partly what I wrote before, because the power of Xi must be in the right place. And then we have these other parts here. This is the W, and in the end we have basically the cross. Okay, basically this is the propagator that you get. Remember that we are using the Donder gauge fixing, which was this one. Where F is given by this one. Okay. Now let's look at this propagator to understand actually which are some of the degrees of freedom that may be important of shell in a process, for instance, because propagator can only doesn't appear only as a non-shell. I mean, the graviton does not appear only as a non-shell propagating degree of freedom. But if we look at perturbation theory, we construct diagram and so on, the gravity also appears inside loops, internal lines of a scattering and so on. So there could be components that actually are important in a computation, although they don't appear as on-shell degrees of freedom. And in particular, for instance, if we consider some amplitude that we contract, where we take the propagator and contract with some SSG tensor, some of the components will go away because of conservation law, basically, as I wrote there, right? Because you can have P mu, T mu nu equal to 0. And this will be all the terms, for instance, that will have omega mu nu times T mu nu. Why? Because remember that omega mu nu, where I wrote it, there. Omega mu nu is proportional to P mu nu, P mu P nu. So if I multiply P mu with T mu nu, which means omega mu nu with T mu nu, I will get something that does not contribute to the amplitude. And you can see that all these terms here are proportional to this type of omegas. The only one that do not contain these omegas are these two. Because if you look at them, these are only proportional to thetas. And theta mu nu times SSG tensor is not 0, will contribute. So in this sense, actually, even if you have an abdo, for instance, even before going on shell, you will have actually two components that will be important. And these are a spin 2 and spin 0 components, which give you, if you want to count them as off-shell degrees of freedom, there would be 6 components. And actually, very interestingly, if you take an amplitude, T mu nu propagator T rho sigma, and you go on shell, you should expect to find the 2 degrees of freedom. And actually, this spin 0 part here is very important because this spin 0 will cancel the longitudinal part of the spin 2 part component. Because you see, here we have +2, +1, 0, -1, -2 components. This one will be responsible for this 0 here. Otherwise, if you go on shell, you get the wrong number of degrees of freedom. And you can show that explicitly by doing computation. I can give also a reference where I did that actually for in some papers completely. And it's nice actually because you say, oh, then there is some meaning to this spin 0. It should be there. Indeed, for instance, let's suppose you want to forget about this spin 0. If you forget about the spin 0, you will not have any more. You will not have any more a theory of gravity with 2 massless excitation. You may, for instance, a massive theory of gravity if you only have the spin 2 here. And actually, this is the reason. If some of you have heard about this Weltman Van Damme discontinuity, there are several ways to see that. In terms of the spin projectors, it's very clear. It's super clear because the propagator for a massive graviton will be only this one with a mass here. The propagator for a massless graviton is this one. And you see, if you take the limit, if you put a mass, you put the limit m going to 0, you will never recover only the massive gravity. You always have this discontinuity here. Okay? Okay, good. So to conclude this part of the previous lecture, the message is the following. It's true that a propagator on shell has 2 degrees of freedom, but off shell, you have, let me say that, 6 degrees of freedom. Okay? Of course, they are not off shell, they are not on shell physical degrees of freedom, but let's call them off shell degrees of freedom because they're important. So it's like you are propagating off shell 6 angular component because you'll have 5 here and another one here. 6 angular momentum as if it was. Okay, good. Are there questions about this? Yeah. Yeah. Yeah, good. So the thing is that you see, if you look at the action for h mu nu, like I wrote it yesterday, right? The action, it had this type of term. There was minus plus h mu nu box h mu nu, right? But then there was also minus h box h. You see already at the level of the action that the trace has the wrong sign if you want to see it as a field. And this is what you also see here in a way. But this 0 here in the end on shell is a gauge degree of freedom. Does not propagate. Is constrained as degree of freedom. There is no propagation on shell for this field. Okay. Indeed, what I just said, if you take an amplitude that you contract, you will see that indeed this one is important to cancel something else. Okay. So that's why it's not really a propagating cost. It's just a degree of freedom that is going away when you go on shell. Yeah, I think it's also related to that. Yeah. Yes. Okay. Yeah. PR? Uh-huh.
Expand the spherical harmonics and write the graviton properties.
You mean you go in this axial and polar things? I've never done by myself, but I think there are, people that did, right? These people that did it in black hole space-time, they did that, I think. So you say you don't work with eta mu nu in Cartesian coordinates, let's say plus minus. Go in another coordinate system where eta is not anymore minus 1, 1, 1, 1 by something else. Well, one should do the computation in that case and see what you get. Yeah, I don't know. But in that case, eta will be different because you will get some r square and yeah. So it will be completely different, I think because the components will not be invariant in that transformation. Yeah, I'm not sure. But I guess you can do everything in any coordinate in general. So you just have to do it and see what you get. But in the end, whatever it is, if you compute some invariant object, like an amplitude, you should get the same result, whatever you put there. Once you contract all the indices. Yeah. Oof, 23 minutes already. Okay. Okay. Okay, I hope this part was clear. And I suggest, if some of you has never done this computation, I think it's nice to see, especially this one of the cancellation between the spin 0 and the 0 longitudinal mode. Just do the same thing I told you, like there, for instance. You have to take the amplitude with this propagator. Only this one will be surviving. But don't take an on-shell graviton. Take an off-shell graviton. So you don't impose p square equal to 0. For instance, you can take a time-like vector. Just take p 0, 0, 0. Okay? If you do that, you will get what I said. Okay. Now let's go next. So the point was that yesterday we wanted to do free theory and today interactions. And of course, with interaction, as also Anna said yesterday, computation can be very chaotic, very complicated because you have vertices, graviton vertices are crazy. And indeed, here we are not going to do any type of hard computation. But the point is, without doing hard computation, can we anyway extract good information about like the high energy behavior of Einstein general relativity? And the answer is yes. Before going there, before actually having a break of a couple of minutes, in these last 10 minutes of this first part of the first 1 hour and a half, let me quickly say something. Of course, now we derive the on-shell degrees of freedom, right? We said there are two. And what you do usually in QED is say, okay, I know which are now my physical helicity, let's quantize them. And the canonical way to do that, you say, okay, I have my field and I expand it in like wave planes on a infinite superposition of wave planes, plane waves, plane waves, and you promote h mu nu to operator, right, as you do with the photon. You may write something in terms of the frequency of the photon, of the graviton in this case. And you have to sum over the helicities, +2 and -2. You introduce annihilation and creation operators. So you will have, for instance, an annihilation here that depends on helicity as well. You will have some polarization that depend on the helicity, a wave plane, and then you will have also the complex conjugate. Okay, now this is just a free field, of course, and you can, in principle, quantize free fields in an easy way, in principle. Imposing commutation relation, for instance, for the annihilation creation operator will be something like this. This is 0, and then you will also have dagger, which is 0. I don't write them, yeah. And then the one that will not be 0 will be the A dagger. And if you put, for instance, something like this, you may have, using some of the convention, something like this. Okay, now this allows you also to define a vacuum state in the free theory. At least you can say, okay, for instance, I want to define my vacuum state, this one, the one that is annihilated by the unique Poincare invariant state that is annihilated by this annihilation operator. And then you can construct, for instance, single particle state or two particle state and so on, which are populated by graviton with momentum p and helicity lambda by acting with the A dagger. This would be called, for instance, a one single particle state with a graviton that has momentum p and the helicity lambda. Fine. And then in principle, you can say, okay, now here I can add interactions and go on, as we do, for instance, for QED. But the thing is that things are not so trivial, because when you have nonlinear interactions, things can become more complicated. Especially, for instance, if you just take this Lagrangian with a gauge fixing at h mu nu, and you do computation, and you compute some loop diagrams and so on, you end up with violation of unitarity. Why is that? It is related to the fact that basically something is missing in this theory. And this something that is missing, in general, can be, not in general, can be solved by introducing the so-called Faddeev-Popov ghost fields. Now, there will be no time to really go into details. I'm not even sure if I can do something complete, but the question, how many people are not familiar with the Faddeev-Popov ghost fields? Okay, one? Okay, everyone is familiar then. Okay, good. Well, then I can say something quite quick, and then I will try to, yeah. So the point is the following. Okay, let's stay here. Perfect, I'm happy that this image. The point is the following. Let's just, so usually these div Popov fields are introduced to basically remove the gauge degeneracy of the path integral. We will never do that here. We'll just try to motivate them, actually in the way they were motivated historically by Feynman, which is the following. Because you see, in the first part of the lecture yesterday, I mentioned unitarity and optical theorem. Let's just take again the optical theorem in a way that I wrote it yesterday, which was twice the imaginary part of an amplitude. Was equal to the sum of all possible intermediate states of something like this. Okay. And you see, one way to write it diagrammatically, for instance, let's suppose you take just a one loop diagram or something like this. Let's say you want to compute the imaginary part of this loop diagram. What is basically telling you this optical theorem that this loop diagram somehow will be proportional to some square of this amplitude. Basically, optical theorem just telling you that, okay, you take this, you cut it, and you can show that is equal to the square of a three-level amplitude, which has no loop inside, for instance. Okay. Now, the thing is that in the procedure of this cutting, as I said before, right, a propagator, when it's off shell, can have both on shell physical ellipses and also ellipses that are not propagating off shell, right? Now, when you cut this, you should make sure that what you get here, so in these intermediate states, n, in this sum, which is everything you can get here. So one way to write this is like this. Let me be more specific. No, this is not what I want to write. This was what this is something like that, right? And this would come from this cutting that I showed there. Okay, the returns you are cutting, and you get this type of amplitude square. And basically, when you look at the right-hand side of the optical theorem, here, when you contract, you have only the physical on-shell states, right? You say, I'm preparing something at in some stationary flat, in some region like at infinity. I prepare it, I scatter, and I get something else at in another asymptotic region. But here, when I sum on n, any type of state can be here because these are virtual states, intermediate states that can go through these loops. So there could be physical on-shell particle, also this non-physical on-shell that can appear still as off-shell degrees of freedom, for instance. This is the same for non-abelian gauge theories. You may have this type of diagrams with closed gauge loops, and you can have something like that. So when you cut it, you may have this internal line that becomes external. And so this external line can carry like also on physical ellipses. So you have to make sure that these processes here in the unitarity relation are cancelled by something. If you do not add this something, you will violate unitarity. And what is this something? This something are the so-called gauge, the so-called Faddeev-Popov fields. Okay? One can derive them just by starting from path integral consideration related to gauge invariance. But the amazing thing, I think, in my opinion, about Faddeev-Popov field is that at the same time they solve gauge invariance problem and unitarity. And unitarity actually is really important. You should not violate it. And this was first noticed by Feynman by doing computation actually in gravity, and then also in non-abelian gauge theories. He noticed that there were these problems when you have this, for instance, closed loop of gluons or gravitons and so on. So the point is that, making the story short, the gauge field, the Faddeev-Popov fields must be introduced in the Lagrangian to make sense of interaction. Voila. And let me just write what this Lagrangian is, at least in the case of gravity. The full Lagrangian that we should write down is something like this. We will have the Einstein-Hilbert action that we imagine to expand in perturbation, like you always have to keep in mind that we are going to do some expansion of this type. Then there will be, in my notation, the gauge fixing. And that will be this Faddeev-Popov action. And this Faddeev-Popov action basically is related to the variation of the gauge fixing function here with respect to the parameter or function that we are using in the gauge transformation. So the FP is given by the following expression. Basically, we have these anti-commuting fields, which are the Faddeev-Popov fields. Let me call them FP fields. There will be this functional derivative with respect to the zeta nu, where this zeta nu was the one that appeared in the gauge transformation for the perturbation. And here there will be some C nu, and these C nu satisfy anti-commuting relations. So these are a bit funny fields. Although they look like bosons because they have these vector indices here, they have anti-commutation relation that vanish. Now, of course, again, here I should write a double integral here with the y4, because here I should put an x, here y, then there will be a delta Dirac that appears, it cancels one integral when you take the derivative. We don't do that. We just imagine that we just have one, otherwise we go crazy. And now you see, the point is, first of all, okay, we have this Lagrangian, and of course, in order to really determine the form of this SFP, you must specify who is the F mu. So given a gauge fixing, you will have an associated Lagrangian for the Faddeev-Popov fields. Okay, yeah, I'm not sure. I don't know if it's more or less clear, the logic, because it's fine. At least the physical logic, like why we need really these Faddeev-Popov fields. Okay. Now, okay, we're not going to do much. Let's just say a couple of things about this gauge, these Faddeev-Popov fields. First of all, we can write the Lagrangian for them, the action in a suitable form, in a more suitable form, which is basically, let's use integration, the chain rule here. We can write something like this. Okay. And remember the transformation for this object here was something like this, right? Gauge transformation. And so if we use that, we will get something like this. Yeah. Minus sign there, it will be. And then here there will be basically just this covariant derivative with some delta that appear. So you will have, rho nu sigma plus sigma nu rho acting on this gauge Faddeev-Popov field here. And then just using the remaining things, you will have the following. Now, that's what you get. And of course, to really specify the action, you need to give some F mu here, otherwise we cannot do anything. And now let's actually, since we mentioned what time is it? Okay, 5 minutes and then we stop. Since we mentioned the Faddeev-Popov, since we mentioned the gauge fixing in two cases, the covariant and the non-covariant, let's see how it looks like just in these two cases, since we have them, right? So remember, let's first do the covariant, the Donder, which was this one. Was this one, but since you have to take this functional derivative, it's useful to write it in a different way. We have the whole operator acting on the field. And this can be done just by opening the trace here and using some delta Dirac, the Kronecker delta and so on. So you have, for instance, something like this. Okay, it will be mu rho sigma plus mu sigma rho minus 1/2 mu sigma rho. No. So that's an equivalent way to write it, right? We just used symmetrization and symmetrization of this first term, and we open the trace. Okay. Now we have to take basically this functional derivative. It's simple because you just remove these up to a minus sign. So in this case, what you get, so if you just plug everything in, you will get SFP in this covariant gauge will be basically, see here, you have some symmetric object. Use the symmetry of this, you will get twice the same. But then you have 1/2 and 1/2, so all these 2 and 1/2 will go away. And you have to just contract things. You need to be careful that you have covariant derivative and partial derivatives. So background derivatives and total derivatives. Sorry, you have background derivatives that are partial and full covariant derivatives that still have to be expanded in H. Yes.
Sorry, could you remind me with the minus sign?
Because here we're taking basically a functional derivative. You have derivative acting on H. So when you take a functional derivative, you will have like derivative with respect to the field minus derivative with respect to the first derivative plus derivative with respect to the second derivative and so on. Yeah. And the same here, there will be another minus sign that cancel. Yeah. Because you have first derivatives. Okay, so okay, we need to plug this inside here. Okay, and see what we get. Time is short. Instead of doing the computation, let's just see the result here. Otherwise, we take too long time. In the end, we will get something like this. Okay. And what we are interested actually, just let's try to expand in perturbation now up to linear order in H. So we neglect. If we do that, we will get the Minkowski kinetic term for the Faddeev-Popov plus interaction with H. And if you do that, basically we'll get the following plus H. Okay. So you see what you get is basically some kinetic term for the ghost of this type plus interaction with H. And this interaction with H, so with the graviton, are the ones that are responsible and important that you need to take into account in order to really preserve unitarity and everything. Now, one point, of course, why they're called ghosts. I'm not completely sure. I think the name ghost should come from the fact that they do not appear as on-shell states, but only as internal loop degrees. They don't appear as on-shell states, but they only appear through loops. So we never see them, so they're ghosts. Somehow they hide inside the loops. But later, at the end of this lecture, we will mention again the word ghost, but we will have a different meaning. So please remember there. That's why I don't know why the other one will be called ghost, but this one, I think the word ghost is very suitable because somehow something that's not appear on shell, but all through loops. So somehow they hide themselves. Okay. But it's important to keep in mind that there will be this interaction that are responsible to cancel things. Okay. Now, if you want to look at what is the expression for the other gauge fixing, the non-covariant one, I'll just give you the result otherwise. But you can do it simple. This again, you just take F menu for the. In the other case, you would have this one. You remember was this one, we can write also this in a symmetrized version, which is useful to take the derivative with respect to a symmetric object, which is h mu. Well, this is not needed, but okay. So that's the gauge fixing here, the function you get there. You have to plug and take the derivative. In the end, you will get something like this. And again, here you can expand in perturbation the covariant derivatives. You can identify the kinetic term of the Padif-Popov fields surrounding Minkowski plus interactions. If you do that, you will get the following. There will be yes, this object here plus this object here plus interaction with H. Okay, so you can see now that the kinetic term, yeah, let's do kinetic plus interaction like this. Okay, there will be a kinetic term of this type that is look messy, but that's what it is. I said that gauge fields with interaction may lead to these things because you have to preserve unitarity and also take care of gauge invariance degeneracy in the path integral. And you try to solve this problem by adding these Faddeev-Popov fields. That's what you get. These Faddeev-Popov fields will cancel unphysical degrees of freedom. So the unphysical ellipses, for instance, that would appear as external heads when you take a cut in the unitarity relation will be cancelled by this basic contribution for the gauge field from the Gauss fields, because, for instance, you may have contribution of this type, right, where this is a loop of Gauss. And when you cut it, also the Gauss will have some external part that will cancel something else. And of course, this construction can be also made at the level of the Hilbert space with something that is called BRST quantization and so on. But we don't need anything of that. The only point is that, you see, to really preserve unitarity, we should make sure that the Faddeev-Popov fields does not appear on shell. Because if we cure the things that would appear when you cut, okay, fine, you cancel things. But in the optical theorem, I said that you can also contract just with some on-shell states. So you should make sure that in your Hilbert space, the physical one, in the states that you use to compute amplitudes, there is no ghost. Because if there were a ghost, then you are again in the same problem unitarity, because then externally you may have something which is physical. So some of the ghost contribution will cancel something, but then there will be something else that still appears. So you should also make sure that basically these ghost fields do not appear on shell. And to do things consistently, you have to do, for instance, some projection and define some physical Hilbert space and so on. But what is nice also about this non-covariant gauge is that explicitly you can see that this one does not propagate. And that basically the three level, I would say, unitarity is satisfied automatically. And since it is true, it's a non-shell statement, and it's true in one gauge will be true in any other gauge. Okay. And before doing that, we take a couple of minutes break. So what we'll do in the next 10 minutes, we'll just discuss briefly unitarity, just doing a couple examples. And then we'll move on to loop divergences. Okay. We are 1 hour. Okay. Do you have any questions about this? I know it was fast and I didn't go maybe into details, but the point was that we need to introduce something else to the gauge fixing Lagrangian. That's not enough. Okay. You may wonder why we don't do that in QED. Some people wonder because, actually no. So, in QED, usually we don't do that, but in principle, also in QED we need that. Because in QED, if we work with a linear gauge fixing function, which means that in QED you will have a gauge fixing. Let me say this. Okay, so For instance, in PhD, what we usually do, we add something like this, right, to the Lagrangian. Which means this will be a product of F, where F is this object which is linear in A. Okay? And since you have an object that is linear in A, okay, it's fine because you will never introduce any possibility to have nonlinear interaction for the gauge field A, which will give you some closed loop of photons, for instance. And what happens in this case, if you introduce the ghost fields from the path integral, these Faddeev fields, they will just appear with a kinetic term and no interaction. So they decouple completely. And you can understand that very quickly, very easily, because if you take the transformation for the photon, which is this one, this one is independent of A. So when you take basically this variation, when you take this variation with respect to lambda of this one will not have any contribution that is proportional to A. So basically just a box, just because of this. They will not, this transformation will not give you here anything that basically, when you take the derivative, will give you an A. And so the ghost in that case will only be some C bar box C, and that's it. There is no interaction. So that's why you don't need it usually in canonical computation, in canonical quantization. But actually, that's just because we are choosing this gauge fixing. For instance, if you take this following, you can say crazy gauge fixing, but still is a physical gauge fixing. Sorry, it's still a consistent gauge fixing. For instance, you could take this one. F square. Okay, that would be, this is the Lagrangian. Gauge fixing Lagrangian, which is this one. You take F equal to this plus another gauge fixing omega and mu and mu. This is an allowed gauge fixing that you can add. It is nonlinear in A. If you do that, you will generate, when you take the square, quartic terms in A and cubic term in A. Indeed, if you do that, you may check that basically you have to add a Faddeev-Popov field with a kinetic term of this type plus an interaction term of this type. So you will need this interaction to construct loops of Faddeev-Popov that will cancel some of the loop diagram that you will create with this extra nonlinear interaction. Okay, so when people are saying QED, you don't need the Faddeev-Popov because they decouple, that's true, yes, but only when you choose some gauge fixing, which is the proper one. And also, there is another thing to say about Faddeev-Popov field is that you may say, okay, I said that canonical quantization does not work the way it is because if you just do computation, you generate something which violates unitarity. But actually, canonical quantization is equivalent to Faddeev-Popov quantization because you can always choose a gauge. You can always find a gauge which is, for instance, the so-called axial gauge, in which the Faddeev-Popov fields completely decoupled. So in that gauge, you prove the canonical quantization and this other way to proceed, they are equivalent, so the two approaches are equivalent. You may say, can I do also that with gravity? Can I introduce an axial gauge in the same way we do with the non-abelian? Unfortunately, gravity is a bit more involved because there is a paper by Kapper and other people where they say that if you introduce axial gauge for gravity to decouple the ghost, you can do that, fine. But then you generate non-covariant quantum terms, which complicate the renormalizability. So that's why people think never use this axial gauge in gravity. But anyway, these are just words for people who maybe know about axial gauge and so on. Let's stop for 2 minutes, and then we'll discuss unitarity. Yes, question.
The only thing for gravity, there's also linear and edge. Then the gauge should happen in this case.
No, because Basically, this is the action. You have covariant derivative here.
Around that space,
No, but the thing is that the full action will have the covariant derivative. Then you expand in perturbation, and there will be a kinetic term plus. Yes, because basically the thing is that when you, this is the Faddeev-Popov action, where this is the object that will contain the information about the covariant derivative, okay? And indeed, this will bring the following relation. So here it's like I'm taking, you can do that even for a generic background, which is not Minkowski, some G bar. We'll have covariant derivative bar, and then also covariant derivative without bar. At the zeroth order, you recover just the kinetic term for the ghost.
you basically write the transformations not around that space.
No, because I just took this one. Yeah, the full one. To higher order. Yeah, that's what I mean. Yeah, to higher order. Yeah, taking into account this higher order's contribution.
Your action gauge fixing is gamma mu lambda lambda equals to 0.
My gauge fixing is
Linear form.
no. You can even take the linear form, even this one. It's fine. With the nonlinear one, you will have a different story. It will be different because you may have the extra contribution in the transformation. Yeah, in this transformation, basically. Here. So let me write it maybe more explicitly. This one, yeah.
Or if you are working with the theory around flat space time, then your gauge invariance is not that. It's just telling you not provided any.
No, but it's like you see, you have the full action, right? But you introduce a gauge fixing, which breaks everything. Some f pop that will be determined by the gauge fixing. And the full transformation that keeps this invariant is not the one with partial derivative, but will be this one or it will be, for instance, this one. Plus kappa, and there will be plus yeah, I mean, there is the combination of three terms when has to create them. Yeah.
The basic is covariant derivative is the background. It's not the
Here is the full metric. Is the full metric here. Here is G plus eta plus H. Is eta plus H. Or G bar plus H if you have a different background. It's like engage non-abelian gauge field. It will be partial derivative, the standard one. Then you will have the covariant derivative as well, which has the gauge field inside. So it will not be just partial. There will be partial and some covariant derivative. Okay, we can. But I think maybe for the gauge. But please, let's discuss later. I will be happy.
You need all this because you want to present manifest Lorentz invariant.
Sure.
If
Yeah.
you go to light-on gauge, you need.
Yeah, I'm not familiar with the light-on gauge now, but okay.
But of course, you
So what? Just for my ignorance, what would you impose as a gauge fixing for the light-on gauge? Is the same?
have to fix the gauge. You eliminate all the non-physical degrees of freedom.
Yeah, because you have in mind an approach based on S matrix. where you just do it at the level of the S matrix. But if you start from a Lagrangian, the procedure say that you have to add some gauge fixing. That could be either like, I don't know now in the case of light cone, but if you start from a Lagrangian, somehow you have to add a gauge fix and then consequently a Faddeev Popov in general. At the level of the S matrix, I can understand that maybe since you work on shell, automatically you should see some cancellation that has happened already, the unitarity is preserved by itself. And maybe in the case of string theory, that's what you do. You don't really need this, maybe.
You need, if you want to preserve manifest Lorentz.
Mhm.
If you go into the light cone gauge, people have computed loop diagram in light cone gauge.
But still like from a Lagrangian? Okay.
Theory.
Okay, I'm just not familiar with the light cone gauge. I see. I mean, for sure, in the axial gauge, you don't need that because they decouple. That's. Okay. Well, I never seen it, so yeah. Then if it's the same, I understand what you mean. Yeah, because in axial gauge, you don't need that. But I guess even there, with axial gauge, in some cases, I would say, especially with gravity, things get complicated when you do computation. Yeah.
As far as I know, it's only up to one loop. I don't know if people have computed two loops.
Explicitly, I don't know. In gravity, for sure, no. I don't know now.
It's indeed don't use the, I think, axial gauge to do an exact, calculation of the metal spectrum.
They use
An axial gauge, yes.
okay.
Maybe even generic, maybe it was like.
They go to higher loops.
Okay, I think let's start again because. Yeah, let me just mention, since you mentioned axial gauge, I said something. So I think the axial gauge, when you impose axial gauge for the following, we'll add something like this with some nu mu in some direction. Usually people take the third direction, right? And if you impose this gauge fixing and do things correctly, you can show that basically the ghost field will decouple. In gravity, you could do something similar. You could, in principle, add something like this. In principle, a gauge fixing. But instead of the gauge fixing decouple, the ghost field decouple in this case, but things become more complicated in terms of divergences because I saw some paper that people say that you can generate, well, will be clear later, but some loop counter term of this type, for instance, which are a bit messy. So that's why people don't use it in gravity, at least from a field theory perspective, this axial gauge. Okay, anyway, let's go further. Okay, so you remember at the beginning, when I will introduce some brief elements of quantum field theory, there was a list like locality, symmetries, unitarity, renormalizability. Now, the Lagrangian we have been writing so far, they are local, right? Because they contain only finite order derivative fields. Of course, you may expect no locality through quantum correction because you may get like logarithm of box, logarithm of p square, which are fine. But the bare Lagrangian that we start with, they are local. Fine. So that principle somehow is still satisfied. Then symmetries. Okay, we have explored a bit what symmetry do, and actually symmetries lead to a series of things, right? Physical degrees of freedom, gauge fixing, Faddeev Popov in general, and so on. What was the other one was unitarity. Now, unitarity, again, want us to prove it, and so on. And in perturbative quantum field theory, usually you take the optical theorem and you prove it perturbatively. And of course, you have to make sure that things cancel. Now, really, in 5 minutes, there are two things that we can check as a check unitarity, at least at 3 level. First is that, for instance, if we take the simplest amplitude you can imagine, just a field h mu that propagates freely. Of course, you can compute what is the amplitude of this propagation. And if it's negative, it's not good. If the probability is negative, you would have anyway some positive probability. Positive, sorry. You would like to have some positive contribution, because otherwise the optical theorem would be violated. As I said the first lecture, do you remember? We had basically imaginary part of something positive in some cases, and so that must be true also for gravity. And what we could imagine, if we just take an h mu nu that propagates from one point to another, and it propagates with some propagator here. If you go to momentum space, you will have the polarization that appear here with some, polarization, and you will have some polarization, complex conjugate, polarization, and you can compute an amplitude. You may consider this as kind of vertices. You will have some Feynman rules also for this type of simple amplitude. In the end, for this amplitude to go to from 1 to 1 will be something like polarization tensor, propagator, polarization tensor. And then using the Feynman diagram that with the rule convention I'm using here is like for each vertex I put a minus sign, and then the whole amplitude will have also a minus sign and so on. So in the end, we'll have an I here. So you should expect that the imaginary part of this amplitude must be positive if you want to satisfy unitarity for what I said. Here you can use any propagator we want. Let's just take the covariant one, which is minus I to here is square minus. Okay, now there's a problem with the epsilons here. No, let's not. I mean, I'm using the epsilon for the prescription here and also the epsilon for the polarization. I should maybe change this in the notes. But keep in mind these are different things. Okay, this is the epsilon for the. Let's call it Carly epsilon. Yeah, yes. This is the epsilon for the shift, and this is the epsilon for the polarization. And here you will have mu rho nu sigma plus mu sigma nu rho minus mu nu sigma epsilon rho sigma. Now, if you do this computation, contracting everything here, what you will get is 1 over p square minus I Carly epsilon, which is the shift. And then you will have this object minus this object here, where epsilon here is the trace. Good that I put. This is the trace. Okay. Now you want to evaluate the imaginary part, and again you have to use basically simply you can use this formula. It is equal. Okay. If you use that for the propagator, basically you go on shell because somehow the pole at the imaginary part of the imaginary part here is really picking up a delta. It tells you that the propagator is carrying some physical freedom shell with pole p square. This delta here will be p square, and p square equal to 0. You know that when you go on shell, for the analysis we did before, in the end we'll only have 2 degrees of freedom, which are physical, with the trace equal to 0. So this will be neglected, and you will only be left with this object. Okay, and this is something positive definite. Okay, so somehow you are consistent with unitarity. This is one check on unitarity. It's good to do since we mentioned unitarity. The other check we can do, trace. Yeah, because basically, you see, when you take the imaginary part, you have this delta of p square, which means that you are somehow going on shell. And you remember the analysis that we did for the polarization, when we computed on shell, we got basically this expression, minus 1, 1. So the trace is 0 on shell. And so basically we get something which is positive definite, which is good. Right. So if you use a standard prescription of quantum theory, you get still something that is somehow perturbatively fine in terms of unitarity. Another thing that one could check, as I said before, which is fun, that's it here, is the following. Now we have a kinetic term for the Faddeev-Popov field, which is the one in the non-covariant gauge. And you may ask, can we, for instance, just compute the propagator in that gauge and see what we get? Yes, of course, we can do that. And for instance, without going into much details, what happens is that basically you could write for the zeroth order term of the Faddeev-Popov fields in the gauge something like this, for instance, which is useful. Some kinetic operator for the Faddeev fields, and you can write it also in as we did for simplicity. You can go in this system here. So spatial momentum along the third axis. And if you want to write this in matrix form, it will look like this. As you can see, the P0 never appears in this way of writing it. So if you invert it to compute the propagator, you will never have anyway any P0. So basically, there is no way in which you can form a pole at P square. So this is consistent with unitarity, because you should not expect any Faddeev-Popov field that propagates as an on-shell degree of freedom and as a pole on shell at P square equal to 0. And it is very nice because with a non-covariant gauge, you can see it very easily without computing amplitudes or without making a projection explicit and so on. You just see it here by doing this analysis, which is nice. Okay, so this was just a few words about unitarity that I think it was good to say because we mentioned like principle quantum field theory, right? Now, what's next? Well, I was planning to do that already 20 minutes ago, but now we should start discussing a bit of loop divergences in Einstein theory in the framework of perturbative quantum field theory. Fortunately, Anna yesterday already mentioned something. For instance, she presented an example of scalar fields interacting with, correction to graviton. Anna considered some process of this type yesterday, where you have matter fields inside and a graviton outside. And already this type of interaction, she showed that could lead to some basically terms which are not already present in the initial Lagrangian. What we're going to do here basically is mostly focus on pure gravity without matter and try to see what type of divergences we can get. We will do an analysis. What is that we're going to do basically? We will never do explicit computation. We will just try to determine the structure of the counterterms. We'll try to determine, when I mean structure, like the invariants that are present in the counterterms, and also what is the whole of the divergence you get, for instance, in dimensional regularization. And what is that then is left to compute? Of course, is the coefficient. But the coefficient needs really a computation, which takes lots of time, can be very involved. I cannot even say I'm super technical to reproduce it here. But it's not needed for the purpose of understanding really what happens at the loop level. So basically, the nice thing that we will see is that just by using arguments, symmetries, and power counting, we'll be able to basically determine everything we need. Yes, so 5 minutes. Let's just mention something to start. And after this, I hope I will finish really maximum now and like 30 minutes of the second part, because then the rest will be to deviate from Einstein general relativity and try to see whether we can do something better. Again, we discussed locality. And we is that. We discussed some symmetry, and they're very important, right, to do many things. We discussed unitarity quickly. Let's discuss now renormalizability, which is the other thing that is very important to constrain consistent Lagrangian in the framework of perturbative quantum field theory. Or better than consistent, I would say, like more predictive Lagrangians. So let's go back to our Einstein inverted Lagrange. We said that, okay, we expanded in perturbation. So we had a kinetic term plus, now let's forget about gauge fixing. I'm just saying schematically. Plus, there will be basically interaction that will start with a power kappa. Let's remember that kappa was defined as 8 pi g. So this is dimension of 1 over mass. Sometimes 1 over g, as Anna rotates, is written in terms of the so-called Planck mass, which has a value, which in principle is not even clear if it has really a physical meaning, but it could. Is really of this type, 10 to the 18 GeV. But anyway, just to tell you that this coefficient here has a dimension of a mass, we can write it as 1 over mp, just to keep in mind there is a mass there, or we can keep kappa. But if we look at the interaction term, a generic one at any nth order in the field H, there will be some structure of this type with always two derivatives. Why two derivatives? Because H is scalar is always proportional to second derivative of the metric. So whatever expansion we take, we will always have maximum two derivative in any order in the interaction. Good. So now you can immediately see. Let's go back to what we said in the first lecture. How to check whether a theory is renormalizable, non-renormalizable, or whatever. Take the dimension of kappa for all the interaction terms. The dimension of kappa will be n minus 2 times dimension of kappa, right? Now, dimension of kappa is -1 from here, right? Because this is a mass. So what we get is 2 minus n. And of course, interaction starts from 3. So this is always negative for all the possible interactions you have in Einstein gravity. And that's why Einstein gravity is said to be perturbatively non-renormalizable. I emphasize perturbatively non-renormalizable because there are also approaches that try to make sense of renormalizability of Einstein gravity non-perturbatively. And you will hear a lot of that from Benjamin and Alessia's lectures. And also during the program, if you're around here, there will be talks on that. We can also understand better why renormalizability fails somehow. We have 2 minutes. I'll do this in 2 minutes. For instance, you can imagine, let's just take a generic loop integral, where there will be a certain number of vertices, a certain number of propagators, a certain number of loops, just schematically. For instance, you may have L loops. And we imagine that we are working even with the covariant gauges where, for instance, even the Faddeev-Popov field have box in the kinetic term, so 1 over p squared in the propagator. And you will have, in general, in a loop diagram, you will have integration over loops. Then you may have generic propagators, let's say E propagators. And then you may have interaction vertices. Let's just assume the worst case, which is the one where you have the graviton vertices, because they have two derivatives. They're higher in derivatives in general. Well, actually also the other, but anyway. we take this. So you will have V vertices. And you can look basically just by power counting at high kappa, high k, how this will behave. Just doing some power counting. Just schematically, this will be some k to the power 4L from the loops, minus 2i from the propagators, and plus 2v from the vertices. This can be written like 2L plus 2L, so I'm just taking 4 equal to 2 plus 2, minus I plus V, right? This is just the same. And now we can use the topological identity that usually relates loops, internal lines, and vertices in a diagram. So basically this relation. Okay. And what you get is that cap K grows like 2L plus 2. So basically, increasing the number of loops, the divergence of this integral becomes worse and worse. So somehow this also suggesting that something is not so good at energy in gravity, at very energy. And this is related basically to the fact that theory is not renormalizable, and that basically at any order loop in perturbation theory, you have to add new counterterms to renormalize divergences. And we'll discuss counterterms after the coffee break. Okay. Indeed, it is 1 hour, 31 minutes. We can stop here. See you in 30 minutes. I mean, see you now. But if there are questions, we can discuss also now.